All right, so let's look at today as an application, band limited processes. So we say a process is band limited if its spectrum is obviously confined to a bandwidth. So the way I have noted, in other words, the spectrum is zero. This is the beyond a certain maximum frequency sigma naught. So such processes are band limited. What I am going to do is the corresponding stochastic process x of t, I'm going to develop a sampling theorem very close to what you have studied in the for deterministic signals. Remember, the issue is here we are not dealing with the deterministic signals. We are dealing with the stochastic process. So the question is, if I sample the stochastic process, can you reconstruct the stochastic process in some sense, in some reasonably close values? So what is the theorem, etc. So that's the, so we are going to do this as a application. As I said, this is not a deterministic signal. So, but the theorem will be very close to the deterministic signal case. So let me take this, let me show you an interesting result, and then I'm going to use this result to prove the sampling theorem, stochastic sampling theorem. So this is x of t is a stochastic process, a band limited stochastic process, band limited. So in other words, its spectrum is like this, some minus sigma naught to sigma of a. So of course it means the process is Whiteson stationary, etc. And then we pass it through two different filters. I'm going to call the outputs to be y1t and y2t. Except these filters have the property that h1 omega and h2 omega are equal in that where the signal is. So I'll draw a picture. What I'm trying to say is, so the spectrum is like this, some minus sigma naught to sigma. This is sxx omega. Then the two filters are like this. So this is h1 omega and h2 omega. The two filters are not equal. They are only equal within this band. So if within this band, let's say they are like this, some shape, same shape. But here you have different shape outside for the first filter. The other filter is like this. It also has a different shape here. But these two filters are not equal. So if you call h1 to be the inverse transform of h1 omega and h2t to be the inverse transform of h2 of omega, then obviously h1 of t and h2 of t are not equal. So the filters are completely different. You have a filter here h1 of t in time domain, and here you have h2 of t in the time domain. And so h1 of t may be like this, h2 of t is completely different in time domain. But so look at the input. You are taking a stochastic process and passing through these two different time domain filters, but they are not completely different. If you look into their frequency spectrum, within the band of interest, they are equal. So the question is, what can you say about the relation of y1 and y2? So let me take their difference to be et. So et is y1t minus y2t. And I'm going to compute the mean square of et. So before that, et is y1t minus y2t. But y1t, look at here, y1t is, we studied this, right? This is a linear system, an input coming through linear system. So the output is x of t convolved with h1 of t. And here x of t convolved with h2 of t. And we know the cross correlation, autocorrelation of the output, etc. So this is x of t convolved with h1 of t minus same x of t convolved with h2 of t. As you know, convolution is a linear operation, so I can write this as h1 of t minus h2 of t. And if I call this to be h of t, I can write this to be x of t convolved with h of t. So anybody going back this, so if x of t is, of course, we started with the spectrum. So it's a Whiteson stationary process. A Whiteson stationary process going through two linear filters will generate, anybody? What about the output? Hello? Whiteson's through linear filters, the output will be?
The same, Whiteson stationary?
Yeah, output also will be Whiteson stationary. So both are Whiteson stationary. If you look at this, how about ET? Look at this. It's like a Whiteson stationary going through another filter H of t. So ET will be?
Again.
Whiteson stationary. So how do you write this in terms of the autocorrelation function of E expected value of ET squared will be what? Autocorrelation function, evaluated it? 0, right. And how do you express that in terms of its spectrum? Anyone? You remember this? Yes or no? Why is that true? That last relation? Anyone?
I mean, it's inverse Fourier transform?
Yeah, it is inverse Fourier transform evaluated at tau equal to 0. So that is true. So so look at this expression. Let's evaluate SE omega. Anybody? How will it? E of t is, this is the expression. So what will be SE output spectrum will be what? Anyone? How do you write the output spectrum in terms of the input spectrum? Someone please, let's move on.
It's input multiplied by transfer functions for transform.
Input what? Input means what?
Like, let's say input is SXXW multiplied by HW.
Multiplied by HW, this is what you learned so far?
H square.
Yeah, H absolute value squared, right? The transfer function squared, right? Let's not get sloppy here. This is not W, this is omega. Let's plan to read things as they are. Now, what is H of omega? Anybody? H of omega will be what? I mean, we have been writing H of omega. How do you get H of omega? Look at the definition here. Capital H of omega is the transform of H of t. So H of t is H1 minus H2. So H omega will be what? Anybody? In terms of the two transforms, H1 and H2. Capital H1, capital H2. Huh?
H1 omega minus H2 omega.
All right, now look at the picture. So how will the picture look like? Remember, H1 omega and H2 omega are equal within the, look at here, the picture. H1 omega and H2 omega are equal within this region. So the difference will be?
0.
What?
Difference will be 0.
Difference will be 0, right? So this will look, the picture will look like this. So this is our original spectrum. And if I draw below this, the H1 will look like this, H1 minus H2. This will be H omega squared. It will be 0 here. So from here, SE omega will be the product of this. What will you get if you multiply these two? Anyone?
Zero.
What is it?
It's 0?
Yeah, 0, because look at here, this is the expression, right? You multiply these two spectra, but one spectrum is non-zero here, the other spectrum is 0 where the other one is non-zero. So this will be identically 0. So look here, I take this and put it into this expression, then this will be 0. So we have expected value of ET squared will be the area under SEE omega will be 0. That means ET is 0 in the mean squared sense. Look, if a signal energy is 0, the signal cannot be non-zero in anywhere with any reasonable, any non-zero measure region, because then this value would have been non-zero. So we say, but ET is the difference between Y1t and Y2t minus Y2t. So we can say Y1t is essentially the same as Y2t. So we write it like this with a dot on the top. So this is mean square sense. The difference between Y1t and Y1t is essentially, or mean squared sense, same as Y2t. So look at this result. I'm going to use this again and again, or at least one more time. If a band limited signal passes through two filters which are identical transform within that band limited region, then even though the filters are different, the output will be essentially the same, or the mean squared sense the same. Anybody has any problem with this? Otherwise, I'm going to move on. So I'm going to show you an application. I'm going to use this result to prove the sampling theorem. So look at this. This is in transfer domain, a capital H1. H1 omega is just a delay. So this output is going to be xt plus tau. Right? Because look at the transform of Fourier transform of xt plus tau will be what? Will be integral e raised to, I'm sorry, x of t plus tau e raised to minus j omega t dt. T plus tau I'm going to put to u. So t plus tau is u. So t is u minus tau. So this will turn out to be integral xu e raised to minus j omega u minus tau beta du. So that will be e raised to j omega tau xt or xu e to the power minus j omega u du. So this is the Fourier transform of x omega x of t. So we have if the transform is e raised to j omega t, then the output will be delayed by plus tau. Now what I'm going to do here is I'm going to find a equivalent expression for here. Remember, we are starting with, this is the key, I'm going to start with a process which is band limited. So I'm going to start with a process which is band limited. That's where the sampling theorem comes in, right? And I have H1 omega. H1 omega is just a phase shift, e to the power j omega tau. What I'm going to do is, in this region, in that region minus sigma no, minus omega naught to omega, sigma naught to sigma, I'm going to find a different function which is equal in this region. So in this region, of course, I want this transform to look like this, a linear phase shift. But outside, I don't care. Here, this function goes on. Here, whatever it is. So the easiest way to generate another function is I am going to consider H2t to be the Fourier series expansion of, I'm going to consider a periodic representation here. In other words, consider a periodic representation. So H2 omega is the periodic representation of this function. This is the over this region, e to the power j k omega tau, right? That's the periodic representation of H1. All the periodic representation means one will be a periodic representation. So they will match in this region. That's all I want. So here the period is 2 omega naught. I'm sorry, this will be t. So this t is of course 2 pi divided by the period, which is 2 omega naught. So this t is pi over sigma naught. This t, we'll need this later. So remember, this is not in time domain. This is, everything is in frequency domain. This is frequency domain, frequency domain. I hope you understand what I'm trying to do. See, I'm going to trying to use the previous theorem. So I want two filters which are the same in this region, the region of interest to me, because there is no signal outside. So one is a delayed one, the given signal. So a delayed one creates this one. Now I am trying to find out another filter which has exactly the same transform within the minus sigma naught to sigma naught. So easiest way is consider the periodic representation of this. Then this has an expansion like this. As you know, AK is given by the period, which is 1 over 2 sigma naught, 1 over the period minus sigma naught to sigma naught. The original function, which is h1 of omega multiplied by e raised to minus jk omega t d omega. And this is e raised to, this is known to us, this is just given to us, e raised to j omega tau. So if I put it together, this reads minus sigma naught to sigma naught, e to the power, let's say j omega tau minus kt d omega. So if I integrate that, I get e to the power of j omega tau minus kt from minus sigma naught to sigma naught divided by 2 sigma naught multiplied by j tau minus kt. So numerator, when I substitute the two limits, you get e to the power j sigma naught tau minus kt minus e to the power minus j sigma naught tau minus kt, and here you have 2j sigma naught tau minus kt. So look at the numerator. It is 2j sigma naught, a sine sigma naught, right? Because this minus this, 2j cancels, so I get sine sigma naught tau minus kt divided by, yeah, 2j cancel, so you get sigma naught tau minus kt. But this is a sinc function. So the a case we found out a case. So I'm just going to put the values here. So ak turned out to be sinc sigma naught tau minus kt. So sinc, as you know, is a function like this, right? So our h2 of omega is sigma. Look at here. This is what we have been looking for. So somewhere we said I'm going to, where is it? Yeah, h2 of omega is a Fourier series expansion. So ak is sinc sigma naught tau minus kt. So what is the whole deal now? Whole deal is I have one function h1 omega, which is e raised to j omega tau in the frequency domain. And I have another function sigma ak e raised to jk omega t. If I pass this one, this output is x of t plus tau. This output from here again, this is again another phase delay. So these outputs are going to be sigma ak x of t plus kt. So remember, t is here, capital T is here, pi over sigma naught. But this is back to this this is back to this one. We have two functions which are identical in the region of interest where the signal is band limited and maybe different outside, but then the outputs are essentially the same. So that's what we have created here. These two functions, look at here h1 and h2. These two functions are the same in this region where the signal is non-zero, and they are different, of course, outside. One goes forever, the other one is a periodic function. But because they are the same, these two outputs here must be equal. So we get the expression that x of t plus tau equals sigma akx, so I'll write it this way, x of t plus kt ak. Ak is sinc, what was it here, sigma naught tau minus kt. Now I'm going to put in just a small, so the key here, which I forgot to tell you, key here, this k goes from, in a Fourier series expansion, this is the difficulty or whatever. Where is it? Here. In the Fourier series expansion, k goes from minus infinity to plus infinity. This is not 0 to infinity, minus infinity to plus. So here, minus infinity to plus infinity. Now, if you put a t equal to 0, just put t equal to 0 everywhere. There is no t here, it's all tau. So you get x of tau equals summation t equal to 0. So you get x of kt, k equal to minus infinity to plus infinity, sinc tau minus kt. Now remember, tau only appears here, so put the tau back to t. So I'm going to rewrite this as the last expression. I'm just going to rewrite it as look at here, just change the variable, that's all. Here I had tau, here you had tau, I changed it to t here. And there was no tau here because we got rid of, consequently, so what is the whole thing was possible because these two functions are equal in the region where the spectrum is non-zero. So the process is band limited. Obviously this won't be true if the signal is not band limited. So for band limited signals, these two outputs are equal. That means you can, look at the last expression. You can reconstruct the continuous signal reconstruction from its samples. And that's the stochastic version of the sampling theorem. So essentially this side and this side are equal in the mean squared sense. That's what we have shown. Remember, I am not dealing with the transforms of each waveform because that's meaningless. What is meaningful is the power spectrum. Power spectrum happens to be band limited. So we say stochastic process is band limited, not because each of the individual transforms of each realization is band limited. That's only a realization. We look at the autocorrelation function. We take the Fourier transform. That gives us the power spectrum. That power spectrum should have this property. Power spectrum, of course, we showed it is positive. And it may be band limited, may not be band limited. But if it is band limited, then we can reconstruct the whole signal from its past and future samples. But one interesting thing here is you need both past and future samples. But if you have, so this is like the conventional what do you call, Nyquist theorem. So you can call it the Nyquist theorem for stochastic processes, for stationary, band limited, stochastic processes. So this is another justification to sample a continuous signal if it is band limited, and we know that what it says is essentially you lose nothing provided you sample properly. What is properly? Remember, this t is not arbitrary. This t came from here. So during the derivation I said pi. So this is exactly the, so provided t is faster than, so the minimum value is it need to be faster than this pi over sigma naught, or 1 over twice the bandwidth if you divide by 2 pi. 1 over so t will turn out to be in other words, if you write sigma naught as 2 pi f naught, then t will be pi over sigma naught, which will be 1 over 2 f naught. And that is the conventional thing. So the theorem looks very conventional, like the regular sampling theorem that you have studied for this for non-stochastic cases, in other words, deterministic signals. Here we have a stochastic signal which is stationary, and the power spectrum is band limited. Then we can call the process to be band limited. And then it's possible to reconstruct the reconstruct the continuous signal from its samples. But you need, like in the Nyquist case, you need both past and the future samples. So between these two, there is no difference in the mean squared sense. In other words, if you take the difference and try to find the energy of the error signal, it is 0. That's why I went through this this stuff in the beginning. So go through this proof. Then you can see why we went through that. So I used that property here. We have two functions, two transfer functions which are identical within the region where the signal is has the Fourier transform is not, the power spectrum is not 0. So let me explore this. Usually I stop here, but let me explore this a little bit more. Hello? Anyone? Can you hear me?
Yes, Professor.
Okay. So what I want to explore next is this, whether we can get it. This is usually a limitation, because you have a process. Usually you are here. Let's say this is the present value here. So this is x of t, this value. So the question is, can I reconstruct that from the past samples? These are, of course, the past samples. Look at the theorem above. These are future samples. What this says is, to reconstruct this value, you need both the future and past. So what I want to explore next is reconstruction from past samples. So remember, all these are applications. So of course, whatever we are going to conclude is also true for deterministic signals. So as I said, you are here present, the process is like this, and this value is of, let's say t naught or t naught. So this is x of t naught, this is unknown. Question is, if I sample it fast, or if I sample from the past, is it possible to reconstruct x of t naught from past samples? So I hope you understand what I'm trying to say. You say, what is wrong with this Nyquist theorem? There's nothing wrong, except it uses both past and then future samples. So generally you have collected the data, you have all these past samples are available. So remember, what we call Nyquist rate, I'm going to call it Tn, is your pi over sigma naught. Sigma naught is the bandwidth. So before I proceed, so if you sample with the Nyquist rate, look at here. You need both past and future samples. You need these samples, and you need samples on this side also. But then you can sample the duration. Sampling duration is going to be only need to be pi over sigma naught. But if you are unwilling to use if you don't want to use the future, and you still only want to use the samples from the past, then you can see you cannot use this theorem. Certainly this is not enough. You can't just ignore the half of it. So you have to go back to this data. Then you have to realize that you have to give up something. So what you have to give up is that, so the question we are going to ask is, what if I am willing to sample even faster? Remember, something needs to be given up. You don't have free lunch anywhere. So what I'm asking is, so we'll rephrase the question. Is it possible to reconstruct x of t from its past samples if we are willing if you're able to sample faster than the Nyquist rate. Tn, which is pi over sigma naught. So remember, you have to give up something. So what we are willing to give up is faster than Nyquist rate. So to see whether it is, remember, these are the past samples. So t minus kt, right? Wherever t minus kt, k goes from 1 to 3, etc. So the question is, can I use these samples, t minus, so wherever you are, t, you go t backward, this is small t, you take these samples. And we haven't decided what this t is. Tn is the Nyquist rate. So you can see, if at all we are going to succeed, we surely know that if you are sampling at Nyquist rate, you need both past and future samples. So what do you expect? If you are throwing away the future samples, you are unwilling to use the future samples, should you be sampling slower or faster if you want to succeed? Anyone?
Faster?
What?
Surely it's faster.
Yeah, hopefully faster sampling. Even then it is not clear, but let's see what we can come up with. So let's say this is the Nyquist rate. So most likely what we are thinking is, this is the Nyquist rate, so we may have to sample fast. And so we are somewhere here, t. And so the new rate I'm going to call t. T is the new sampling rate. So we know that just from common sense, most likely it need to be faster than the Nyquist rate, which is pi over sigma naught. Remember, we are dealing with a band limited signal. This is the power spectrum of the band limited signal. And this is the new sampling rate. This is x of t. We want to reconstruct x of t from its past samples. So when past samples means it will be like this, right? K goes from 1 through infinity. Look at here, minus k. So this will be all past samples. So this is my reconstruction. So question is, what is AK? So I'm going to, you will see why I am going to select it without telling you any reason now. So this is what we mean by reconstruction from using only past samples, right? So let me take this AK to be minus 1 to the power k n choose k, and you will see the reason. X of t minus kt. And we want this to look like x of t. That's the whole point. We want this quantity to look like x of t. So if I take the if I take the difference between these two, maybe this is k minus 1 here. So let me take the, let me call the error to be x of t minus z n of t. So let me go to next page. Oh, so error is x of t minus z n of t. And remember, z n of t is this expression. So when I put another minus, this will become k. So this will become x of t plus summation minus 1 to the power k. I absorb the minus here. N choose k, x of t minus kt. K from 1 through n. Sorry, I'm sorry. We don't want to go through n at this infinity at this point. Let me take a finite number of samples from the past, especially I put n here. So k goes from 1 through n. K is not 0 because we don't know the value of x of t. So all the, from wherever we are, we using the past samples. Up to, let's say I use up to some n samples, t, 2t, etc. So I use this much data. That's what I'm called. And we want that to look more or less like ZT. So I'm going to see what happens to this error. So notice the key is now, because when you put k equal to 0, of course you get x of t. So I'm going to absorb this inside. I can rewrite like this. That's the whole point. I hope you see this, right? What I have done is, this is your estimator. This is your actual value. The difference is this. I absorb the minus 1 here. And if you put k equal to 0, minus 1 to the power 0 is 1. N choose 0 is 1. This becomes x of t. And so this term, I can absorb it inside by extending the k to 0. This is the key here. Look at here. This was 1 here. This is key. Error can be written like this. But now look at this. I can write this as, this is only a delay. So I can write this as like this way. Because if I convolve with a delta function, x of t becomes x of t minus kt. So I can rewrite like this. X of t minus kt is delta of t minus kt convolved with x of t. So let me call this to be h of t. So the error signal now can be written as x of t convolved with h of t, where h of t is this quantity. So let me look at h of t. H of t is summation k equal to 0 through n minus 1 to the power k, n choose k, a delta of t minus kt. So if I take the transform on this side, h of omega, the filter, remember, transform is a linear operation, so minus 1 to the power k, n choose k. Anybody knows what is the transform? If delta t has a transform which is flat, so what is the transform of delta t minus kt? Anyone? Fourier transform properties. I just did it a few minutes back. Hello?
e to the j2 pi kt.
E to what?
j2 pi kt. Is it
E raised to minus j
k?
k omega t. No, 2 pi. With this, but anybody sees this? This is an expansion of something. Anybody sees anything? See, look at this. N choose k. Yeah, minus 1 to the power k, minus 1. There is a power to k. So what is this expansion of? You have to be able to see a few things. Anyone? And you have k equal to 0 through n.
1 minus exponential j omega t.
Exponential what?
J omega t.
What
minus,
about this?
minus j omega t, yeah.
Very good. So you see, that's the whole point. All right, so let's go. We found out h of t. So anybody here, E of t is like this. E of t is the output of a filter whose transfer impulse response is h of t, and input is x of t. So what is the power spectrum of the output? Anybody? How do you find the power spectrum in terms of what is the expression? Anyone? We know the transform of this H omega. So the output power spectrum is? Hello? This spectrum, output power spectrum is what? Tell me, let's move on.
X omega times
Sx omega,
X omega times H omega square.
yeah, H omega squared, very good. H omega is here. So I'm going to, Sxx omega multiplied by H omega squared, this expression. This will become 2n. So let me take this expression and see how far I can simplify that. So 1 minus e raised to minus j omega t to the power 2n, right? So I'm going to pull out from here, I'm going to pull out j omega t by 2 outside. So this will be e raised to j omega t. This is a standard procedure. Absolute value to the power 2n. I hope you see that, right? So because of the absolute value, what is this quantity? E raised to x, e raised to jx minus e raised to minus jx. Anybody?
2j times sine omega t over 2.
Yeah. When you take the absolute value, what is the absolute value of this term? Anybody? What is the absolute value of this term?
1.
1, right? This is absolute value is 1. Absolute value of j is 1. So I hope you see that this expression is sine omega t by 2 to the power 2n. This one. So I can put it into SEE omega. Why are we doing all this? Because we wanted to see the output. So this is the input spectrum multiplied by this quantity, 2 sine omega t by 2 to the power 2n. Absolute value to the power 2n. This is this is the expression between the output spectrum. So remember, I wanted to see, I want to see, look at the logic. I want this error to be driven to 0. I want this error signal to be driven to 0, this error. So if error signal to go to 0, then what should be the mean squared energy of E of t? Anybody? What we want to do is REE0, which is the area under SEE. We want to drive this quantity to what? Anyone? Talk to me. Remember, look at the logic. I want this. I'm suspecting I want to make this reconstruction look like x of t. So if I take the difference, which is the error, I want to drive this error to 0. If the error signal is absolutely 0, then what will be the mean squared energy, expected value of E squared t? That will be, we want this quantity to be what? What is our desire, I am asking? We want this quantity to go to what? Anyone? Hello?
Also 0.
Yeah, we want that quantity to go to 0, right? But that quantity is the area under the spectrum. So that's going to be the 1 over 2 pi Sxx omega. Well, remember, listen to this argument now. Now this is very carefully done to the power 2n. What will be the, here I put the limits as minus infinity to plus infinity. But remember, this is a band limited process. This goes from minus infinity to plus infinity. But because of the product, what will be the limits here? Anybody?
Minus sigma naught to
So that's the key. We only need to integrate. Look at this energy is exactly the same as integral from minus sigma naught to sigma naught, because this thing is the first expression is band limited. This expression is band limited. And we don't need a positive. We want to drive this quantity to 0. Look at here. We don't have any control here. We have no control here. We don't know what the shape is. But we have control here. Where is our control? Our control is only, we have control over t. T is the sampling time. You can sample, you can decide sampling rate. Not sampling rate, sampling period. The sampling period is under your control. So look at here. This quantity is raised to the power 2n. So if I can, so let me rewrite that quantity there. I have 2 sine omega t by 2 to the power 2n. So this is something like epsilon to the power 2n. This quantity is the epsilon. So if you want this quantity, so if you want the quantity on the left side to go to 0, this is not going to go to 0. You can try to make, or the only thing is this question is by controlling the t, the sampling period, can you make this quantity to go to 0? For this quantity to go to 0, epsilon should be surely what? What should be the magnitude of epsilon if you want this quantity to go to 0? Anybody? Epsilon should be a quantity to the power something. If you want that quantity to go to 0 as n becomes large, then
Less than 1.
Huh?
Less than 1.
Less than or greater than? What did you say?
Less than.
Yeah, less than, not greater than. I don't know what you said earlier. So we want 2 sine omega t by 2. Oh yeah, before that I should also say one more thing. Look at here. This spectrum, yeah, that's fine. This quantity should be less than 1 for omega less than, so there is absolute value everywhere. I don't need absolute value around 2. Omega less than omega naught from this expression. So this is the same as saying that sine omega t by 2 should be less than half for omega less than. So sine goes like this. Sine expression is like this. So omega less than sigma. Now listen to the argument. So the sine goes like this. Sine of the argument is omega t by 2. So what is the maximum? Say sine is increasing, right? So the as omega is increasing from 0 to sigma naught. So you want this, what is the maximum value of sine for what value of omega? Anybody? Omega is sine is an increasing function. So this will be less than what? Anybody? For this to happen, what is the maximum value of sine omega t for what value of omega? That's what I'm asking. Sine. Omega only goes from 0 to omega naught. So where will have the sine the maximum value? Anyone? Huh?
Pi over 6.
No. That's not what I'm asking. Just answer this question. Omega t, sine omega t will have its maximum value for which value of omega? Omega goes from 0 to sigma naught. Look at the sine curve. As omega increases, this is for different values of omega t by 2. As omega increases, omega can only increase up to sigma naught. So where will be the peak value for this occur? For what value of omega?
Pi over t.
What?
Pi over t.
I know, but we may not even go to pi. Omega only goes up, look at here. Omega only goes up to sigma naught. That may be somewhere here, who knows? So what value of omega will this peak? That's what I'm asking. For which, see, look at it. Sine omega t will have it peaks at omega equal to omega 0. Isn't this true? That's why I said you have to listen to my argument carefully. So I'm saying sine omega by 2, absolute value, will be less than sine sigma naught t by 2. Is that true?
Yes.
And so for this expression, look at the logic now. For this expression to be true, we need this to be true. If this is true, then this is automatically true, right? We only wanted this to be true for all omega. So all we have to guarantee is that the maximum frequency satisfies this expression. Okay? Yes?
Yeah, okay.
Yeah. Now look at this. That's easy. So you just need to see which angle will be sine. Which angle is at sine equal to half? 30 degrees, right? That's pi over 6. So that means sigma t over 2, sigma naught t over 2 should be less than pi over 6, 30 degrees. Because sine 30 is half. So we got a, remember, we got a condition on t. T must be less than pi over 6 multiplied by sigma naught and 2. So 2 cancels. Here you get 3. So you get 1/3 multiplied by pi over 6 sigma naught. But pi over sigma naught is the Nyquist frequency, Nyquist rate, Nyquist sampling period. So that means you should, if you only want to use the past samples, you should be sampling 3 times faster. So let me write down if so to reconstruct x of t from its past samples, then t must be at least 1/3 of the, t must be at most 1/3 of the Nyquist period. That means you must be sampling at least as fast as 3 times the Nyquist rate. Nyquist rate is 1 over Tn. So 1 over T should exceed 3 times 1 over Tn. This is the Nyquist rate. And this theorem, you can, if you look at it, I just used this constants, AKs. You can try to, in fact, you should go home and try to use some other clever function, and you can easily show that you can make a slight improvement over this. It's definitely clear. There is nothing you can do below Nyquist rate, but if you are willing to sample faster and faster, then you can actually stay away from the future samples and reconstruct only using the past samples. So I've done a couple of things now. I gave you the sampling theorem, the conventional sampling theorem, stochastic sampling theorem, and I also showed you a different method of, opened up a possibility of reconstructing the signal from its past samples. Now, I want you to go home and you can think, actually you can do it. You can think of some other constants here, so that some other coefficients here. This is like a window, right? So essentially I'm doing something like a window and x of t minus kt, x hat of t. So this is where the freedom is, k equal to 1 through n. So this will go to, so what you want to do is think of some other weight function instead of this. Maybe using multiplying by k or 2 weight functions together. The whole idea is, can you improve it such that I don't even need to sample as fast as 3 times, maybe 2.5 times is enough, maybe twice is enough. And indeed, such results are possible. See whether you can think and get it through it. Then if it is something new, that's something new also. But there are results even generalizing this. And you can look into this reconstruction from past samples. But the idea is still, you may be able to create your own windows where you can do it faster than even not. You don't have to do. So this is as fast as 3 times. This is one reason in CDs, etc. The oversampling is done, because then the reconstruction from Past alone becomes easier. Any questions? Otherwise, I'm going to move on to a different topic. Any questions there? Hello? Yes? So I'm going to ask you to go home and see whether you can think of some other beta k equal to 1 through n, x of t minus kt. So that t is, of course, t is smaller than tn, but it's still greater than, let's say, 3 times tn. So can you do something better than what I just showed you? You definitely can, but see whether you can think it and get through it. Any other questions? Anyone?
Professor, why we need to reconstruct xt?
I mean, remember, for example, audio, right? I mean, if you want to reconstruct the analog signal, you have to do from the. So the question here is x of t is analog, right? And x of kt is discrete samples from the past. So if you want to play music, etc., that's you definitely want the continuous signal, right?
Yes.
So that's one reason. Another reason is you can think of this as an estimation problem. If I give you, look at here, I'm not giving you any autocorrelation function or anything. I'm just giving you past samples. So this is like saying I give you all the past samples. How do you reconstruct it from? Look at these windows here. I mean, if you look at your what we have done, so a couple of ways you can think of this as an estimation problem because you are here, this is t equal to t naught, this value is unknown, and if I give you all these values in the past of the signal, remember, so this is x of t minus kt, some t, this is x of t, we don't know this value. So I want to estimate, so this is the problem, estimate x of t from its past samples without knowing the autocorrelation function, etc. We don't know anything, we just have these samples. So generally, if you look at our estimation, we will look at the covariances and the filter will turn out to be in terms of the covariances. Here, what I am trying to say is that even if you do this, this is a pretty good approximation, minus 1 to the power k minus 1, n choose k, x of t minus kt. Look at it, this is only past samples. This has nothing to do with covariance. It's just a regular filter, constant filter.
Okay.
So the interesting thing is this filter is good whether it is your voice or my voice. Depending on every problem, you don't have to change these coefficients. Any problem, you can use the same thing for reconstruction. So this is a good reconstruction using the past samples, using a signal independent. This is this signal independent filter. If you look back or even today's exam, the filter will turn out to be signal dependent. Whatever is the autocorrelation and the variance of the signal will play a role. Here there is nothing like that. That's the beauty with the Nyquist theorem also, right? Nyquist reconstruction, the filter is just to sync values. It doesn't matter which signal. So, you know, if you have a filter which is going to depend on the signal, then it is messy, right? Like the match filter. It depends on the filter.
Yes, yes.
So that's the advantage here, right?
Okay, thank you.
Yeah, so this all comes under the broad problem of estimation, forecasting. So, but the most important property of the Nyquist theorem is that one is you can reconstruct the signals from band-limited processes. And the second is the filter values, the coefficients are independent of the signal. Of course, you need a band-limited signal. If the signal is not band-limited, this is not going to work. So that's what it is. So this is another way of looking at estimation. So if you have some sort of data, data available, and if you know that its spectrum is band limited, then one way to estimate is using a filter which is independent of the data. So then you can go for something like this. But of course, then you have to worry about how to implement these coefficients because it involves factorial. So that's a different issue. You may have to do some clever cancellation and implementation in some ways because these values will become larger and larger. And so you may want to think about. I gave you one idea. See whether you can come up with some other combination where you don't have to go as fast as 3 times. There are results out there, but before you look at that, you start thinking and see whether you can do it yourself. And that could be a homework problem. In other words, come up with some coefficients where you don't have to you don't have to sample as fast as 3 times. Any other questions? Anyone? So this is another aspect of what we just covered is another aspect of signal estimation for particular signals. So they are band limited signals. So they are already Whites and stationary. So remember, they have some behavior, Whites and stationary and band limited. If none of this is true, you go back to what we studied earlier. You can always find a linear filter. But then the coefficients are going to be signal dependent. You need to know their autocorrelations and so on. And certain you have to solve for the certain matrix equation and so on. So if you know more and more about the signal, if you know it is stationary, you know it is band limited, then you can get away with the filters which don't depend on even the signal. But then you may have to sample very fast. Remember, somewhere you have to give up. As I said, there is nothing free. So what we are willing to do is sample like crazy. You are willing to sample faster and faster. And usually nowadays with all the high switching circuits, that may not be an issue. Because then you can say sampling faster is very cheap. If I can get away with a filter which is not data dependent. Think of what we are saying. If you get a filter which is not data dependent, then once you design it, any signal you can reconstruct by passing through the same filter. That is not the case with the previous techniques we studied. Linear prediction, generally those coefficients AKs are dependent on the autocorrelations of the. Remember, previously we had we said x of n is what was it? Or x of n plus 1 is sigma ak xk, k equal to 1 through n. But these AKs will turn out to be the solutions of A1. Remember R0, R1, etc. Rn. Otherwise, it may be even non-stationary, right? Equal to gamma 1, gamma 2, the cross correlation functions, and you have to solve them. But these AKs are going to depend on this. This is the expected value of xi, xj star, etc. Here, there is nothing of that sort. These filters, these are the AKs, which has nothing to do with the signal. That's the beauty of the sampling theorem. Any questions? Any more questions? Anyone? Hello? Tell me yes or no. Shall I move on or do you have any other questions? Is anyone listening? Hello?
Yes, Professor, I can hear you.
Okay. Do you have any questions?
Yes.
Then what is it?
No. We can move on.
Okay, very good. So let me move on to something, another important idea in stochastic processes, the question of ergodicity. So what does that mean? So remember, if you look at the power spectrum of any process, that's the Fourier transform of autocorrelation function. If it is discrete, then you need to use this expression. Both the way we know this is a non-negative function, etc. So, so if you want to compute the power spectrum, you need to know the autocorrelations. Usually, we may not know these functions. Then we will say that we will estimate these quantities from data. So let's take another example. Let's say the mean value. Mean value is expected value of x of t. So that is x multiplied by fx of x of dx. This is how it is computed. So usually to find the mean value, this is called the ensemble average, right? You need the probability density function, etc. Usually these are unknown. So the question is, even if you take a simple quantity like the mean, how do you, so what I mean by ensemble average is, you know what it is. You have stochastic process is a collection of all sorts of realizations. So if you take any time instant, you need to find the density function there, right, of this. So that will be some function like this, depending on how likely those values are. Then we need to average in this direction. So this is ensemble average, means average in this direction. Average over various realizations. So this is what is usually involved. You have to average over in this direction, in the vertical direction. That's what we mean by ensemble average. And in practice, reality, what is it? In reality, all you have is you observe something, you get one of these samples. So I'll draw it in the next picture, next page. So you have a stochastic process, which is a collection of waveforms. And this is the ensemble average here. I explained to you what is ensemble average. And this is expected value of x of t, just to compute the mean, mu x equal to integral x fxx dx. But in usually all you have is one of these data points. Maybe you collect some data here. So we can do an average in this way. That's what we usually do. This is time. You have one realization. So you can do a time average, and this is what you do usually. Is, let's say, from minus t to t to t. I'm going to call it a mu hat, and I'll put x because we are. So this is a time average, this expression. So this is we can do, doable. This is we cannot do it. But this is what we need. This is what we need. When we say mean, this is what we are looking for. That means the averaging in the vertical direction. But what we are able to do is doable. We can do this, right? Is averaging in the horizontal direction. And this is what we call estimation. We are estimating the mean from the data. Of course, we are estimating. But the question is, this is like apple and orange. This estimation is in the time direction. What we are looking for is ensemble average, this mu x. That's in the stochastic averaging over various density. Usually the problem is you don't know the density function. This density, on top of that, this density function in general depends on t, which value you are looking for. So t may be here, t may be some t not here. We need to figure out the density function there. But usually none of this is available. So we just have one realization. Whatever we measure, that's a realization. We do an average. So the question is, the stupid question we are going to ask is, since I only have the time average, is there any condition under which this time average will look like this, the ensemble average? Is there any condition under which these two will look the same? So if mu hat of x begins to look like x, then we call that such a process to be x of t is, we say, is mean ergodic. So that's the meaning of ergodicity. But as I said, this is time average. This is remember, this is just an average, so it's just whatever it is, it's a quantity, it's a random variable. Mu x of t is not a random variable. And yeah, in general, I forgot to tell you here, in general, this could be a function of t, mu. So what we want is the time average, which is mu hat of x, to look like mu x of t. This is an ensemble average. So first of all, you can see this could be a function of t. This is not a function of t. So this won't make any. For this to make sense, so we must have a constant mean. We must have mu x of t should be equal to some constant mu x. So if you want this to happen, then constant mean is a necessary condition. So the process doesn't have to be Whiteson stationary, but the process must have a constant mean. So then the question is, can the time average, this is the time average, right? Minus t to t, x of t dt. Can this look like the constant mu x? This is unknown. This is the ensemble average. Under what condition this is going to happen? We want the time average to look like the right side. Remember, the right side is the ensemble average in the vertical direction. Time average is in this direction. And so, as I said, generally the two doesn't make any, it's not comparable. But we have, since we cannot do anything else, we want to ask the extreme question, when is this going to look like this, or when are they becoming equal? Notice this is a random variable. On the right side, this is just a number. So the answer is clear. We want a random variable to look like a constant. Anybody? What is the condition for a random variable to look like a constant? Anyone? There are two conditions. Tell me. A random variable has its, think of it, it's a distribution function and density function. But if you want that to look like more and more like a constant, a number, what should be the condition on the random variable? Anyone?
Variance is 0.
And what about the mean? Huh?
Mean also constant.
Which constant? Mean should be equal to what? Remember, this is a random variable. We want it to look like this constant. So mean should be
0.
0. Mean of this is 0. Then how is this going to look like mu x? So mu x, think again, mu x is a random variable. We want it to look like a constant mu. What should be the condition on it? Anyone? Mu is somewhere here. So what will be the condition on the density function of, so you can see it's a density function should look like this, right? Mu x, yes or no? So the density function of this should be look like a delta function, right? For it to, so what will be its mean? Anyone? What will be the mean of this quantity? Look, if a random variable should look like a constant, you said one condition is, of course, you can see the variance should of that quantity you said should be 0. That is true. What about its mean? So it's beginning to look like a constant. So which constant should it look like?
Mu x.
Yeah, right. So what should be its mean?
Mu x.
Yeah, that's, I think, is clear. You can also clear here from here. If the density function becomes delta, the density function this function x multiplied by mu x dx, this becomes a delta function around the mu, then this whole thing integration will turn out to be mu. So the mean should become, so this is the two conditions for mean ergodic processes. So x of t is mean ergodic if this is true and this is true. So I hope you understand ergodicity is a more deeper concept than stationarity, because as I said, for this to make sense, we must have a constant mean is necessary. That's part of the stationary condition, but that's not enough. You need more stuff. So let's analyze this a little more. So for x of t to be mean ergodic, now there could be a problem from this, a small problem in the final exam. So you better try to, because this is an important concept, I want you to understand this. So the first of all, for x of t to be mean ergodic, first of all, the process should have stationary mean. In other words, Whiteson stationary in the first condition. Otherwise, none of this will make any sense. If the mean is different at each time, then by averaging and getting a value is never going to equal to. So you need this condition. And then this is our expression. We want this quantity, which is the time average of a given realization. We want this to look like this. So we want its mean to be, so let's look at its mean. Expected value of mu x hat is 1 over 2t, expected value of this quantity, minus t to t, expected value of x of t dt. This value is mu x. So mu x goes outside, so you have mu x 2t over 2t mu x. So that is, luckily, that condition turns out to be true. So we have expected value of the random variable is mu x. If you use this for the, this is the sample mean. This is called the sample mean. So what is the question we are asking? Question is, when is sample mean when does sample mean represent actual means ensemble? See, this is a meaningful question, of course, because the ensemble mean is what we are trying to find out. Generally, you say, look, I have 10 observations, you add it and take the average. That's what everybody does. So the question is, when does that's what we call the sample mean. When does the sample mean or the time average, this is also time average, when does it represent the actual ensemble average? So the answer is here. We needed two conditions. First of all, the expected value of the time average should be equal to the ensemble average, and the variance should be 0. That's as you said. So we also need the variance of mu x hat of t go to 0. So let's analyze this condition. I'm going to compute variance of mu x hat. That's expected value of mu x hat minus its mean squared. Look here, I hope you are following me. We found the mean of the mu x hat, that's mu x, which is the same as what you are looking for. So you want this quantity to go to 0. So I'm going to expand this. So this is, I'm going to substitute for mu x hat. So that's 1 over 2t x of t dt minus mu x. This whole thing squared. I can bring this mu x inside because mu x is a constant. Look at what I'm trying to do next. 1 over 2t x of t minus mu x dt. because it's a constant, the second integral will be mu x multiplied by 2t over 2t will be exactly this, okay, before squaring. Now I am going to get rid of this square by expressing it twice. So I have two integrals, 1 over 2t, 1 over 2t, so 1 over 4t squared. Then I have two integrals. The first integral is xt1 minus mu x dt1. The second integral is xt2 minus mu x multiplied by dt2. You can put star here if you want. So I'm expected value, I'm going to take it inside. So we have variance of mu x hat equal to 1 over 4t squared, double integral. Remember, each integral is from minus t to t. So that's true here also, minus t to t, minus t to t, expected value of. Now I'm going to leave it to you to do this. We have gone through, if you expand this, there will be 4 terms. And you to simplify, you will get this expression, expected value of x of t1, x of t2, minus x of t1 mu x minus x of t2 mu x plus mu x squared. So when you apply the expected value, this will become mu x squared minus plus 1s. So this expression multiplied by dt1 dt2. So this expression becomes now minus t to t rxx t1 comma t2. Let me assume it is not even White's and stationary. Mu x squared dt1 dt2. We want this quantity to go to 0. So we have a theorem. So I'm going to call this to be the covariance of T1 at the T1 gamma T2, CXX T1 gamma T2. So for a process to be mean ergodic, that means for the time average to represent the ensemble average, we need two conditions. Of course, the time average should be constant. The process should have constant mean. And the second condition is there is a complicated condition on the covariance of the process. This is the autocorrelation function minus mean squared is the covariance function. This is the autocovariance. This should go to 0. So there is additional condition. So what I'm trying to say is it's something like this. If you have stochastic processes, White's and stationary is somewhere here. And strictness and stationarity is somewhere here. But the interesting thing is the mean ergodic processes are here. Mean ergodic processes are so in other words, they have additional constraint. They don't have to be strict and stationary. We just need the mean to be constant, but then there are other conditions. You have this stronger condition. This is a quite strong condition, right? Whatever that means. The covariance is the covariance function should satisfy this expression. Now I can show you some simpler case if you simplify this result. So this is the theorem. This is the theorem. So what is the point? The point is, usually remember, everybody does this without thinking. We measure some data, we add it up and we say here is the mean. What you need to realize is when you are doing that, what do we mean by mean ergodic? That means a temporal average, which is what we usually do, can be used as a substitute for the ensemble average. But it is not free. It is not true all the time. You need this extra condition, and nobody ever worries about this. So consequently, we are averaging. So a time average can replace ensemble average only if you want to do that, then this integral should turn out to be 0. So if the integral is not this doesn't go to 0, then what you are doing is not right. But who cares, right? That's the way people observe. Time average means this 1 over 2t sigma x of t dt, or in the discrete case, simply x of ti divided by 1 over n, I equal to 1 to 1. So this is the discrete mean, this is the continuous mean. Both these are random variables. This random variable can replace ensemble average means expected value of x of t, which is, we are only dealing with the, so you want that to be a constant. Ensemble means multiplying by the density function, etc. And no one has any of that. All we can do is this. So the theorem is an important theorem. It says you can use this to replace this, provided this condition is true. So I hope you understand the additional burden involved. And so you can't ignore this and say this is always true. That is false. So this condition becomes a little simpler if the process is, if x of t is White's and stationary, then I'm going to show, then look, cxx t1 comma t2, which is rxx t1 comma t2 minus mu squared, because rxx t1 minus t2, that's the whole point of White's and stationary, minus mu x squared. So I'm going to call this rxx a tau minus mu squared, and I'm going to call it cxx tau. So the variance of mu x hat, let's see, which was 1 over 4t squared, double integral minus t to t, cxx t1 comma t2 dt1 dt2. So this integration is here. I think we went over this earlier. We need to integrate over a strip like this. So this line is t1 minus t2 equal to tau. Look at here, t1 minus t2 equal to tau. So if you integrate over this, I only need to find this area and slide these lines from this top portions to bottom portion. So this will become 1 over 4t squared. It will become one integral because I'm only doing d tau, just along this. So when I change t to d tau, I'll get a new line, t1 minus t2 equal to tau plus d tau. So I need to figure out this area which I have scaled. I think we have done it several times, because this will turn out to be 2t minus t tau. Right? Remember, this is t1, this is t2, this is tau is in this direction. So how do you do this? You take this point will be tau, and so this small distance is tau minus t. So this big distance is t, so that is t minus tau minus t, so that will become 2t minus tau. So the area of the big triangle is 2t minus tau the whole squared, because base and altitude are the same, multiplied by half, minus the other one is 2t minus tau minus delta tau, the whole square. So when I expand 2t minus tau, the whole squared goes away. Then 2 times 2t minus tau multiplied by d tau plus dt squared. I'm going to neglect that. So that's the area. So notice that this will become cxx tau multiplied by 2t minus tau d tau. This is the area, this area. So the limits are from minus 2t to 2t. So I'm going to copy this expression to the next slide. So you want this variance of mu x hat, which is 1 over 4t squared minus 2t to 2t, cxx tau, 2t minus tau d tau to go to 0. So let me take one 2t inside. So you can simplify up to here. So you want this expression to go to 0. So you can remember we had a theorem earlier. So you can rewrite this theorem. I'm not going to rewrite it. So the new theorem is if x of t to be mean ergodic, we need again two conditions. It definitely needs to have constant mean, and this second integral becomes a little simpler. If the process is Whiteson stationary, then you only need the last expression to be true. So if x of t is Whiteson stationary, then for it to, then remember it naturally has constant mean, then it to be mean ergodic, the necessary and sufficient condition, we need this, I'm going to call it 1. We need necessary and sufficient condition is 1. So this is an extra burden. That's what I want you to understand. This is an extra burden on the process. All Whiteson stationary processes are not going to satisfy that. So,
Professor, are we missing 2t here from the first line to the second?
yes. I'm sorry. There is a 1 over 2t. Right? Thank you. That's very important. Right? So you may say this will be always go to 0 because there is a 2t here. Not true. Because look at here. The integral also unfortunately has 2t. So this could blow up. Who knows? So you have to do this integration. I'm going to show you an example. So the question is, which processes are mean ergodic? So let me give you two conditions. So if a process, remember this is called autocovariance function. If an autocovariance function is absolutely integrable, then x of t is mean ergodic. That's a theorem. This is another theorem. So what am I saying? Anybody knows what do you mean by absolute integrable? What does that mean? Anyone? What is absolute integrability? Absolute integrability means you take the absolute value and integrate it from minus infinity to plus infinity. This value should be some number less than infinity. That's what we mean by it. So you take a function like this. For example, sinc function. Sinc function is not integrable, sinc tau, but it is absolutely integrable. I'm sorry, maybe it's the other way. But you take a function like this, this is absolutely integrable. So suppose, so I'm going to say, suppose x of t is such that, so suppose x of t has absolutely integrable covariance function, autocovariance function. Or if x of t has absolutely integrable autocovariance function, then let's see what happens to that variance. Then variance of mu x hat tau, which is 1 over 2t minus infinity and minus 2t to 2t cxx tau 1 minus, I'm going to show that. Let's compute this quantity. So I'm going to take this is already positive, so I'm going to take an absolute value here. This absolute value is less than, look at here now. I can take the absolute value inside, right? Cxx tau multiplied by the absolute value of this, but I don't need to take absolute value here because this is already less than 1 and positive. Because look at the limits, it's only from 2 to, so you can put a value here, but you don't need it. Now this value is less than 1, right? Because tau only goes from minus 2t to 2t. So this integral is less than 1 over 2t minus 2t to 2t cxx tau d tau. Look at the way the proof goes. But this quantity is of course less than, the integral is less than, integrating from minus 2t to 2t is less than integrating from all the way from minus infinity to plus infinity of the same function. But look at the previous page or somewhere here. If the autocovariance function is integrable, absolutely integrable, then this value is less than a finite number, some m. So this number is less than some m. So this whole thing is less than m over 2t, and that goes to 0 as t goes to infinity. Look, the variance goes to 0, that's the bottom line. Variance of sesame head, if you have this property. So all autocorrelation functions with that kind of which is absolutely integrable is mean ergodic. So to give you an example, let's look at this. So remember, cxx tau is simply rxx tau minus mu squared. So suppose this is e raised to minus alpha tau. It's like this. So you can clearly see it's already positive, and this is an autocorrelation function, and its area under this area, the total area is 2 times the area under one side, and that's a finite number. So this is an example, and even if you multiply here by cos omega naught tau, this is going to oscillate. Again, you can integrate and see all these are absolutely integrable. So processes like this, for which the autocorrelation function is absolutely integrable, autocovariance function is absolutely integrable, they are mean ergodic. For them, you can compute the mean from temporal samples. So for example, the Wiener process, if you check it out, I don't think this condition is satisfied, and consequently, that's not a mean ergodic process. Any questions on this? Otherwise, I have to do a little more using these ideas. So the question is, any questions before I proceed? Anybody? So remember, if I give you an autocorrelation in the exam, and then ask you to show that this is an ergodic process, is this mean ergodic or not? Then you need to compute this. So remember this, for x of t to be mean ergodic, you need to show that the variance of mu x hat goes to 0, which is this. If it is Whiteson stationary, then you need to compute this expression, and one way or the other way, you need to make sure that this is true. So you need to check whether this goes to 0 or not. If it is not Whiteson stationary, you use the other expression that we put a little earlier. If it is not Whiteson stationary, you need to check this expression, 0. So I could ask a problem something like this to check whether a process is mean ergodic or not. So I already told you, of course, if I tell you e raised to minus absolute value of tau cos omega naught tau, from what I said, you know the answer is yes. Anybody, what about if the covariance matrix is cos omega naught tau? Is it mean ergodic? I'm going to leave it to you to think, without that e raised to minus alpha tau. How about the minimum of T1 comma T2? So use that to conclude. So I probably will ask something on this in the final exam. Like a last, remember in the last exam there was a second part which was symbol 2-3 parts. So one of them could be this. The reason I am insisting on this is a very important concept. We all do estimation. You don't even think about it. But and all you do is time averaging in some sense, right? All the data is one sample realization mostly. So whatever you are estimating is under the assumption that the original value, ergodic mean, no, I'm sorry, the ensemble averaged value and the time sample are represented of each other. And that will only happen under a complicated variance condition going to 0. All right, remember, we only talked about mean. So you can ask the same question. How do I estimate autocorrelation function? Remember, autocorrelation function Rxx lambda is expected value of x of t plus lambda. So I want to, this is the ensemble average. I mean, to compute this, actually, I need x1, x2, fxx, x1, x2, then t1 plus lambda, tt comma lambda, dx1, dx2, etc. Usually this is unknown, the density, so the same problem. So the question is how to estimate autocorrelation. So you may say, I don't know this, who cares? I'm just going to do a sample average. Is that true? False? That's what you do generally. All right, so this is also a complicated problem. This is the ensemble average. So generally you will say, I'm going to ignore all this. I'm going to look at here and I'm going to do this. Okay, I'll do it from, and then divide by 2. This is what your hunch will say. How do you know that this is as good as this? This is a time average. This is an ensemble average. And you do, in any case, everybody does this all the time. So what's the justification? So at least for the mean, you saw the justification. Expected value of x of t can be replaced by a temporal mean, provided this complicated integral goes to 0. So technically you should check it. At least you should know that that's the condition under which that can be replaced. So here, instead of developing all new theory, I'm going to do somebody has observed this, that I can use the previous analogy if I call this to be a new process, y of t. Look at here. This looks like the mean of y of t. So whatever I learned before, I can use it here, right? Because this is moved by lambda, so I'm going to use this as, we'll bring back a tau here, but let me leave it this way. Look at here. This is a time function. So if I define y of t, y lambda of t to be x of t multiplied by x star of t plus lambda, a new process. So technically what we are asking for is the mean. So I want the mean of y of t. Then look at the mean of y of t, y lambda of t. That will be expected value of, so mean of y of t is expected value of x of t, because this will be mean of y of t, will be x t multiplied by this quantity. So from mean ergodicity, and its a sample value will be y of x of t. Sample value will be like this, y of t dt, integral from minus t to t, 1 over 2t. Here minus t to t, 1 over 2t. Y of t is x of t plus lambda dt. So you want this quantity to look, so I'm going to call this mu hat of y. This is a constant, this is not a function of t. So definitely previously we know that for autocorrelation function to make sense, you want the mean, this mean to be independent of t. That means the second order stationarity. For this to match this, you cannot have this a function of time. We want this to be Whiteson stationary. In other words, we need x of t to be Whiteson stationary. or at least the second condition should be true. Then we can use this, provided, you know the condition, provided for y of t, you need a function like this, a complicated condition like this. So let me write that quickly, and then we can, so remember, so we want expected value of x of t multiplied by x star of t plus lambda. We don't want this to be a function of t. That means it should be independent of t. So if I call it rxx, then that should be only a function of lambda. Generally, it will be a function of t comma t plus lambda. So for the process to be autocorrelation ergodic, this condition should be true. In that case, this sample average minus t to t y lambda of t, which is 1 over 2t minus t to t x of t x star of t plus lambda dt, will look like rxx lambda if, so let me call this to be mu hat of y, if variance of mu hat, from what we learned, what should happen to this quantity? What is the condition? Anyone? Hello?
0.
Yeah, this quantity should go to 0. So that variance expression is, if you go through all this, what we studied from, substitute from here, this would turn out to be minus t to minus t, cyy, t1 comma t2, dt1, dt2 should be 0. So let's look at this cyy t2. So cyy t1 comma t2 is expected value of yt1, yt2 minus its mean squared, which is ryy lambda squared. So if I substitute for yt1, remember this was xt1, x t1 plus lambda, then x of t2, x. So you can see it's beginning to get complicated. You have star here, minus ryy squared lambda. So even if the process is Whiteson stationary, this may not be, this expression may not be a function independent of t1 and t2. So we say x of t is autocorrelation ergodic if variance of mu y hat, which is 1 over 4t squared minus 2t to 2t cyy t1 comma t2 dt1 dt2 goes to 0. What is cyy t1? You put this one. How do you get the fourth moment? You have to compute it. So remember, the process is already Whiteson stationary. Otherwise, this wouldn't. If so, two conditions. This is the second condition. First condition is it is Whiteson stationary, or at least the second part of the Whiteson stationary. In other words, the covariance function should be a function of t1 minus t2. So everything comes from mean ergodicity. Now, so generally you can't simplify this. Now suppose x of t is Gaussian. Remember, Whiteson stationary means Strickson stationary. So we are dealing with the Strickson stationary Gaussian process. So let's see, and I don't know, you remember this expression? I don't know whether you learned this. For a Gaussian process, if you have 4 random variables, I think we derived this in class. So this is, you get this one. You can write it in terms of the second moments. Look at what I am doing. I am taking 2 at a time. So this expression is true. You plug it in here, call this x1, call this x2, this is x3, this is x4, and then go through this. So In that case, I'm going to do it, so I hope you see it here. Last expression. So the fourth moment can be expressed in as the second moment at 2 at a time, if except t is Gaussian. If it is, of course, stationary, then each of this will be t1 minus t2. So I'm going to do that here. Then cyy t1 comma t2 will become. So let me do it from here. So notice that t1 minus t2. So this will be rxx lambda. This will be rxx lambda. So that's rxx squared lambda. That's the first expression. I took these two. Then I take x1, x3, this and this. T1 minus T2 is, I'm going to call it tau. Then this minus this is T1 minus T2, lambda goes away. So that becomes Rxx squared tau, some tau, where tau is T1 minus T2. And the third expression is this minus this. So this minus this will be T1 minus T2 minus lambda. That is tau minus lambda. And then this minus this. T1 minus T2 plus lambda. That's tau plus lambda. So the third expression is Rxx tau minus lambda multiplied by Rxx lambda, tau plus lambda. And then remember, this was Cx. That's going to be minus Rxx squared lambda. From here, Cxx T1 comma T2 is this whole thing, the fourth moment, minus Ryy squared, no, Rxx, no, Rxx, right? Rxx squared lambda, Rxx squared lambda. So this cancels out. So this turns out to be Rxx squared tau plus Rxx tau plus lambda, Rxx tau minus lambda. So we know that Cyy, finally, I can write it in terms of tau. If that is the case, then I should be able to use this expression for White's. So I know that it's Whiteson stationary, then I should be able to use an expression like this. So you should be able to show that process is autocorrelation ergodic if and Gaussian if this is true. If x of t okay, so etc. So this is the condition for. So the whole point is this is an additional condition on top of stationarity. So what I'm trying to say is a stationary process may not be ergodic. An ergodic process definitely needs a stationarity. Why, at least an autocorrelation, let me qualify that again. If you're talking about autocorrelation ergodic, a Whiteson stationary process may not be all the time ergodic. Yeah, because on top of Whiteson stationarity, you need a condition like this for Gaussian processes. Otherwise, a condition like what we wrote earlier. Something like this. So if a process is, conversely, if a process is autocorrelation ergodic, then it is obviously necessarily Whiteson stationary because you need Ryy to be a function of, not a function of t. So at least the second part. So you can see, so what I'm trying to say is the more ergodicity, the more samples you, average quantities you want to look like the ensemble quantities, you can see what you're asking is more and more ergodicity, and ergodicity is a deeper condition compared to Whiteson stationarity because you need these additional integrals to, in the case of mean ergodicity, you need an integral like this to go to 0 on the covariance function. that may or may not be true. If it is not true, the process is not ergodic in that sense. Finally, let me do one more quickly on speaking of ergodicity. So this is always a question, how to estimate PDFs. Remember, we studied about PDFs in the beginning of the class, or distribution functions. So you need, for a lot of things, you need the PDF or distribution function from data. So the distribution function is, of course, as you know, probability of x of t less than or equal to x. So in general, this will be a function of t also. And you want to estimate this from data. Again, as before, you have just one data set. What do you do with it? This is what we want to estimate. So what I'm going to do is, this x is, remember, you have to compute essentially you want to compute this for all values of x, distribution function. So I want to use the previous ideas, and you can see from here. So I want to use the previous ideas. So I want to express the distribution function as a mean of something. So the question is, can I write the distribution function as the mean of a process? And then look for mean ergodicity. If I do this, you know that this function shouldn't be a function of t. So the first observation is, if you want to estimate the distribution function, you at least need a strict sense stationarity. You need a first order strict sense stationarity. So you see, you're asking for tighter and tighter conditions. This is a practical problem. A lot of places you want to estimate the distribution function so that you can estimate the density function. So the first observation is, if I'm going it as the mean, if I want it to be a mean of a process, you know that for ergodic processes, the ensemble mean cannot be a function of time if you want ergodicity. So if this is the mean, it cannot be a function of x of t. So the question is, how do you get z of t? So look at f of x. So once again, f of x is probability of x of t less than or equal to x. So I'm going to use this idea to define z of t in the next page. So let me define z of t, a new process, to be 1 if x of t is less than or equal to x, and 0 otherwise. So what does this mean? Look at it. X of t may be like this. So x is here, some value. And I'm going to define a new function. This is x of t. I'm going to define z of t wherever this function is less than x. So you can see over this region. So here it is 1. Here it is 1. Then etc. So if I call these regions tau 1, tau 2, and then again, so this goes up to here, let's say. Here, then it goes, and then it starts here again, etc. So you get the idea. I generate this z of t. And why am I generating this? I'll write it here. Look at expected value of z of t is equal to 1 multiplied by probability of x of t less than or equal to x. But this is the distribution function, fx of x. So we got a process whose mean is distribution function. And we want to estimate this from the data. So you just compute the mean of z of t. We want the mean ergodicity for z of t. So we need mean ergodicity for z of t. So expected value of z of t, look at the previous slide, is fx of x, the unknown function. and its mean, sample mean is of course tau I divided by whatever 2i. So if you take some duration 2i, this is what practically you do. You collect the data. For each x, you decide over how long the duration it has been below x. And you add up all the tau i's. This is your sample estimate. You want this quantity to, this is, remember, this is for a particular x. You decided to choose this x. You can choose different values of x. You want this value to look like this. This will happen from what we learned. The mean of this goes to 0. I'm not going to do anything more. Excuse me. So what it means is that the process to be mean ergodic, we want the first order strict and stationarity, because the mean of this should not depend on time. And then we need this complicated condition. So you can go home and try to expand this in terms of the joint density functions and see what the condition turns out to be. It will turn out to be an integral function like this in terms of obviously in terms of the covariance function of ZFT, and in some cases you will be able to translate it into the distribution function or the joint distribution function of the original process. So complicated conditions. So if that condition is true, then we call the process to be distribution ergodic. So once you get the distribution function, you can numerically integrate or differentiate and find out the density function, etc. Or you can that's so if you want that's one way to go, and this is the and again you can see it's not freebie. Every time you get some data, you cannot compute the distribution function. It only makes sense if it is a first order strict and stationary distribution function. So I covered mean ergodicity, autocorrelation ergodicity. We looked at for Gaussian case it comes some so remember, and distribution ergodicity. So variance of mu z hat x will turn out to be what? 1 over 4t squared minus t to t czc t1 comma t2 bt1 dt2 should be 0. So what is czc t1 comma t2? So this is expected value of zt1 multiplied by zt2 minus fx x squared. But what is this quantity? This is z. Remember z of t. Z of t was this function. Z of t is 1 when x of t is x of t1 is less than x. So this is going to be 1 probability of x of t1 is less than or equal to x, and another one when x of t2 is, that's the only time when this is going to be 0. So this is going to be obviously the distribution function of x1 comma 2 second order distribution function at x comma x, but t1 comma t2. The second order distribution function minus fx squared x. So you need you take this function and plug it in here, and there is a 2 integral, right? Minus t to t dt1 dt2. So this one when plugged in here, if that goes to 0 divided by 4t squared, then the process is this is the condition for distribution a probability distribution ergodic processes. And you can go on. So for any function you are looking for, you can similarly find out when you can replace the the ensemble average with the time average. Any questions? Hello? Hello? Everyone, otherwise I'm going to stop here. Is there any other